All right, everyone, welcome back for lecture 2 of perturbation theory. Since the room is empty, I can maybe speak with a little bit of an unmuffled voice. So you may recall that last lecture we talked about perturbation theory and how that is for a situation where we have a problem, a chemical system with a known Hamiltonian that is perturbed, say, by an instrument, or we're going to do some examples like an electric field. Maybe you're making battery materials, and so all of your chemicals will be in an electric field caused by the potential of the battery itself. Maybe it's an electric field from light, so you're doing spectroscopy. Light will perturb the electrons in a molecule in a way that the molecule is not the same. Now, in either case, it may be relatively facile to know the molecular state, the molecular wave functions, and since I'm talking molecules, you'd be using software like Gaussian and whatnot, QChem, games, quantum espresso, there's a zillion of them. So you know this, but the perturbation creates either a mathematical conundrum that can be solved, which is fine, in which case this is why we're doing this, or this is, you can simply in a more facile way, think about what happens to the molecule in the presence of this perturbation. Okay, so we talked about how there are various orders of correction, first order, second order, you calculate energies. From the energies you can calculate the states. It's generally true that most people want to get the energies. The energies are more useful because that's related to your spectroscopy. The spectroscopy absorption energies, for example, are going to be the excited state minus the ground state. So you have the corrections from perturbation theory to those values, and you can relate that to your spectra in a much better way. I don't see too often people saying, oh, and here's the associated corrected wave functions. People just kind of, you can do it, people just don't really care. Okay, so to drive it home, because sometimes this stuff seems like, there's always a big disconnect. I've always been hyper aware of a disconnect between showing you an equation and then you actually using it, right? That those can be so different that if you can't actually use any of this stuff, what's the point? So hence all the emphasis I've had from day one on computational, this, that, modeling. So here's what we're going to do today. We're going to be doing an example, and then I'm going to show you something called degenerate perturbation theory, because there's a slight problem in the presence of degeneracies, which take like the hydrogen atom, which has px, py, and pz states, they're all degenerate. There's all kinds of situations where your perturbation may be acting on degenerate orbitals, and you actually have to take a completely different approach, but I'm going to cover that. Okay, so let's do an example of something that you've basically seen before, which is we're going to do, let me write it down, He atom. Remember that from my fourth problem set? Okay, so let's remind ourselves that helium has Z equals 2. That's the nuclear charge. So it has 2 protons, 2 neutrons. The electronic configuration is 1s2, right? So 1s, 2s, 2 p's, but helium is like that in the ground state. And let's see, what else I want to say? Of course, it has 2 electrons as well, right? So I just did that. All right. Now, for the unperturbed Hamiltonian, and I'm going to use a bit of shorthand here that's kind of atomic-like in units, but at the same time not. So this is how you're going to see this written more often than not. Okay, so there's electron 1, here's electron 2, 2me. Okay, kinetic energy for 1, here's potential energy. Now, one thing you should be able to do is be able to read the Hamiltonian to know what's what. You should know that this is the electron-nuclear interaction. You can tell because it's downhill. It depends only on, it's the first electron because only R1 appears in the coordinate, and Z is scaling the electrostatic charge of the electron with the nucleus because the nucleus has 2 protons, not 1. It's assumed that the protons are equivalent. Of course, there's 2 electrons. Again, E squared is not the magic number E, it's the charge of an electron. Okay, so here, sorry, let me call this H because I'll label this as H naught. So this is just a hydrogen atom. This is just this is just 2 separate hydrogen atoms at this point because we're not allowing them to interact. So I could just take the hydrogen atom energy and just, I would double it because there's two protons, and then I would multiply it by 2 again because there's 2 electrons. So anyway, that's a little funky. Okay, now they're interacting, and of course the distance between them is Coulomb's law. And I could have written R2 minus R1 or R1 minus R2, it doesn't matter. Okay, one thing, again, that's kind of funky about this, I've written this in a way that you will generally see Hamiltonians written for what are, you would be called an expert at this point. Notice that I've removed those constants, I don't have h bar squared, so it's assumed that you know it's there, right? So people just don't bother to write it. I find that a little disingenuous, but that's why it's done. Now you may also be thinking, oh, well, this is in atomic units. Kind of, but what's ME doing there, right? ME is 1. So if you're writing this out in atomic units, then the ME would not be 0. And notice that the 1 over 4 pi E naught for electrostatics, notice that that's not there. So that's consistent with atomic units, but remember the charge of an electron is also 1. So this is just kind of a screwed up way of writing this. It's certainly faster, you should be able to read it, but note it's not just full-on atomic units either. So I've always found this a little funky, but that's just how we do it. Okay, now recall that the reason that we have such a massive issue with 2 electrons is because of separability. This term combines the R1 and R2 coordinates such that you cannot write the wave function as wave function for electron 1 times the wave function for electron 2. It's not like that. But we don't know what any alternative could be. We can't solve this. So we're going to do that anyway. So again, we're going to write this as a product of, R theta phi. Notice that I'm having to be careful about labeling an orbital 1 for electron 1, and I am also being careful about, R theta phi for electron 1, also the orbital for the first electron. Here's all the same for the second electron in its orbital. Now, the orbital designation psi 1, psi 2 can go away because they're both going to be 1s orbitals. So I'm being a little disingenuous by labeling the wave functions as psi 1, psi 2 when they're both 1s states. Now, I could be trying to describe an excited state helium atom, and that's why I did that, just in case for some reason you have to do that, but we're out of time. I would have totally put it on a problem set, but we're out of time. Okay. So there's that. So again, I've written them in separable form. This isn't quite correct, but what are we going to do? That means all of our energies will not be correct, but it won't be too bad either. Okay, the angular part for an S state is 1 over square root of 4 pi. Stated here. You have to double check that this is all normalized correctly. Notice that the Jacobian 4 pi r squared, Jacobian part of the integral for spherical coordinates. Notice how this takes care of that because when you're normalizing this, remember you square all this. So notice that the wave functions will take care of the Jacobian part, the 4 pi part. So anyway, my point is that they're simple, they're just constants, they make sense, they simply make sure everything is normalized. So it's easy. Okay. And again, in this case, psi 1 is equal to psi 2. It means that they're both just hydrogen-like states. And specifically, I'll do this. Psi 1 or 2 is going to be, and we've got to look this up. Now I'm going to tell you a little bit more about these wave functions that I said before. And again, this is a hydrogenic. Okay, so R1 or R2, right? That's what that means. So let's see, what do I want to say about this? So yeah, wave functions are rather simple. Note that if you integrate R theta phi, if you integrate either of them, R squared dr. Okay, I believe I put this in this form, and so you would need to have this 1 over 4 pi, 1 over square root of 4 pi there as well. So you have to be careful when you look these up, because this is the correct statement for normalization, but you could also do it this way too. Because, especially for S states, it's the angles just the angular parts rarely play a very significant role in quantum mechanics, which is kind of nice, right? When they do, they become drastically important, which tends to be the case in spectroscopy and in the case we're going to see here. Okay, so what you always have to be careful of, and why I always have you double check your normalizations on those homework examples on Mathematica, is because you can imagine that I'm an internet guy and I'm writing some scientific content just out of the goodness out of my own heart. However, the radial wave function in this expression, guess what, is not the same radial wave function in this expression because of the way that this is fully expanded correctly and this is shorthand. Who doesn't love shorthand? The problem is these aren't the same, they don't have the same normalization constants. You got to make sure you know which one of these two you're using. You should know because you're the one calculating it. And then you need to make sure that you're using the correct normalized wave function given which one of these you're using. So again, I just want to point that out. Be really careful of that because that's a good way to completely mess things up. Okay, so I won't hark on that too much anymore. It's just, again, you know, are you an expert? Do you understand this? Well, you should understand what I said here and be careful enough to verify that you're, depending on how you're solving the thing, that you're using the correct wave function, which is properly normalized. Again, are you including the angles explicitly or not? That's what determines that. All right. Now, we just talked about perturbation theory, which for me is 1 hour in the future, which is kind of nuts. And I thank you folks for putting up with the schedule. You know, I have to spend a little more time at home. Okay, now, I just mentioned that the simple Hamiltonian that we know the answer to, which are, of course, are hydrogen atoms with only 1 electron, what we're going to do is we're going to need to have 2 electrons, so we're going to double the energy. Now, the electrons interact with 2 protons, so you're going to have a z squared, and then here's the energy of the 1s state of a hydrogen atom with its 1 electron. So you can see hydrogen atom doesn't have 2 electrons and its nuclear charge is 1. So you can see how all this works out. And this ends up being minus 108.8 eV. So the big picture here is if we ignore electrons interacting with each other, these are our wave functions, which again just are from hydrogen atom. Schrödinger figured this out in his very first paper on quantum mechanics, and this would be the energy. Okay, now it turns out that this is badly in error. It's extremely in error, and it's going to be an error, I believe, as we're going to see here, by about 30 eV. So plus 30 eV. So remember that this will be an energy raising thing. Electrons don't like to interact with each other. Okay, so how do you do that? All right, so the thing about first order perturbation theory, which is what you are going to want to put in your head 90% of the time, it's fairly rare that I see any kind of description of a chemical system where the system is perturbed, again, often by the experiment, where going beyond first order perturbation theory is necessary, or to be blunt, it's just not done, right? So let me just put it that way. Okay, so what is really nice about the lecture you were in is that the first order correction is really quite simple to think about. It's just simply the interaction of the wave functions with the perturbation. It's the expectation value of the energy given what you've identified as the perturbation. So you can think about your molecule interacting with an electric field. The electric field could be from light or it could be from an electrochemical cell. Here is the two electrons interacting with each other. Let's see. Now notice I'm putting a little sort of. I'm not being very exact here. Let's put d tau. Remember, d tau is when I don't want to write. Okay, I'll be a little bit more careful. I have two integral signs, so I better have two partials. D tau 1 would be R1. R1 squared sine theta 1. dr d theta d phi, and then the same for tau 2. Again, we're experts, right? You are now, you're almost done. But remember, you received a physics level type of education in quantum, which is considered really the best, although I haven't covered enough examples. All right, now notice that you got yourself a Coulomb integral, and you've done this. You've already done this, right? Well, you know how to deal with Coulomb integrals when those electrons are on the same atom. So that was problem set 4. Now, in case it wasn't clear, I don't know if I mentioned this, but everything that we did on that problem set, that long derivation, that probably bothered you until you realized that I really wasn't asking any. I was hardly asking a question at all. You just did it on Mathematica, and you can do this on Mathematica. It's really the same thing. Those are for electrons on the same atom. If they're on different atoms, it actually gets obscenely more complicated, unfortunately. It's something I've been trying to learn to do myself. I was even going to put it in a problem set like I did this one, but I realized it's to some degree you need a math degree. And as I mentioned, when you're starting to describe molecules with quantum mechanics, your knowledge of quantum mechanics becomes not very important. Really, PhDs in mathematics are really the people who ought to be worried about this stuff, not so much PhDs in chemistry. And I know that's weird as heck, but true. Okay, I'm going to put this not with atomic units, because you should know when to just make things one or not, just when to wipe out the units or not. But if I don't include them to begin with, then you could be kind of confused about the nature of the problem. So I like atomic units a lot. I'm always using atomic units, but I like to write things out fully, unlike that thing I put down earlier. Case in point, here is our standard translation set of units for Coulomb's law to like joules or whatnot, right? Permeativity of free space, charge of an electron. Remember, all of that is set to 1 in atomic units. But again, you can see why I want to write this down. Now, you may recall that we had a derivation using an expansion in spherical harmonics. So the way about this is, remember that the problem with this is that you need to have integrals. We're not going to worry about angles. We're going to have an integral of R1 and R2. And all the terms have to either have R1 and R2 in them, and you can't have one term with both. And the problem here is how do you deal with that? How do you separate the R1 and R2 such that they can be migrated into two separate intervals and evaluated separately? That was the nature of the problem. So what you did was you expanded that, you expanded it as a series of harmonics, of spherical harmonics. And anyway, look at problem set 2 if you forgot it. It's really, it's kind of something, you know. I don't, I wouldn't even pretend to know how to begin to, how anyone thought to do any of that, but regardless. Okay, so I see the wave function squared, which is basically the charge density, right? The charge density of the electron 1, that's just where it is. And here is the charge density of electron 2. Notice that I'm not differentiating psi 1 and psi 2 because they're both 1s orbitals. And all the angled parts have already been dealt with, so there's nothing more here. Now recall that there's actually 2 terms. The way that this thing just works itself out. So this is being associated with both. Okay, now we got another double integral. R1 is on the outside, and R2 was on the outside last time. Remember, we had to do a little identity to make the upper limits infinity. And you may recall that both of these will end up giving the same amount of energy. Okay, R2 is on the inside, R1 is on the outside, in bracket for the constants, not that they're just one. Okay, now normally, you know, beginning grad student or undergrad level, God forbid undergrad level, you would see something like that and get angry and confused, maybe even grow up in rage. However, now that we've had Mathematica, and again, I've already written these wave functions down, you would hopefully, you know, maybe struggle a little bit with forgetting how you input things into Mathematica, and EXP, E has to have a capital E. Notice how not hard that is. Notice how you don't really need to know any calculus. So now, at this point, given that you're experts, you should look at this and say, you know, this is really a very simple thing. I can do this probably under a minute. And awesome, right? So I'm not even gonna do anything more with this. So what it ends up being is now I am switching to atomic units. Actually, so no, I'm not. My bad. Because I have E squared as, I'm putting E squared in here. Both terms. So yeah, the reason I wanted to, I'm really bad about units today, aren't I? I wanted to leave it this way because I want to emphasize charge over distance, right? So that's charge squared over distance, which would be energy. Now, this of course would be with E squared, the charge of an electron again being 1. All of this would be in Hartrees, converted to EVs. We tend to use EVs for these calculations. So 34, and therefore the total energy is minus 108, 8 plus 34 EV. That is minus 74.8 EV. And the experimental. So the way the experiments work, people put a helium atom, and what they do is they start energizing it in ways I'm not really quite sure about. I think what they do is I think they use a stream of electrons. So you can make streams of electrons using a light bulb. Take a light bulb, which is in a vacuum, you basically drill a hole in it, and then put a potential a plate with a positive charge, and the electrons come streaming out. Now what you can do is you can have these filters that will only allow electrons of a certain kinetic energy to go through. So what happens is it's not too hard to build a machine with a beam of electrons. All of them have roughly the same kinetic energy. So what you would do is you would pound on a helium atom until it falls apart. And having known the kinetic energy of the electrons, and that's all the energy they have because they have no internal structure, they're not rotating, you can bombard things with electrons and get some indication of how much energy it takes to rip atoms and molecules apart, the absolute amount of energy to strip this helium nucleus of all its electrons. So this is actually relatively accurate because we measure it all the time. And again, now you can see how close perturbation theory, first order perturbation theory takes you. Of course, with the second order correction, you'll be that much closer, and isn't that awesome? Okay, so that's really all I've got to say about that. What do I want to say now? So next thing is, and you've seen this before. Next thing is kind of interesting, and again, this is something that all grad students need to know about. So I'm going to cover it. This is something that's actually slightly simpler. I'm going to talk about degenerate perturbation theory, as I mentioned at the beginning. I'm going to talk about degenerate perturbation theory, and it's actually more simple. Excuse me. Okay, degenerate perturbation theory. This is actually more simple than what we just covered the last day and a half. Although, if you read about it, it will seem way more complicated. So that's the thing. Whenever I've run into a problem where I needed degenerate perturbation theory, I have to stop and remind myself, wait, this is actually the easier situation to deal with. So just heads up on that. It will start out seeming more complicated, and the exact opposite is true. Okay, the reason that we need to know this, and I'm going to switch to Dirac notation. Okay, for the first order correction to n, the end state, so that's ground state first excited state, second excited state. So for any state requiring a correction, the first order correction is this. It's going to be the sum over all states that are not that state. Let's see. And I will be writing this about 1 hour from now, so it's kind of funny that I'm deriving this soon, but not yet. Okay, so this is, okay, so this is the correction, and, okay, so again, how it works is, here is like a hydrogen state, and here are the corrections, and the corrections will involve excited states, everything not the ground state, which makes sense because like the state, let's say the end, psi of n is the ground state, because this is really where you use it. Okay, so the ground state with the perturbation is equal to the old ground state plus this correction. Now this correction term includes all states except the one under consideration, because why would you have the wave function under consideration in this term when it's already present, right? That doesn't make sense. It's here. So these are all the other states that are not the state under consideration. Now, the point of that is, what happens if the excited state energy and the ground state energy, let's say that they happen to be zero, because that happens in the degeneracy. Lots of things are degenerate, like the ground state of a particle in a 2D box. That has degeneracies. So degeneracies happen all the time with atoms. 2s is degenerate to 2p, x, y, and z. So there's actually 4 degenerate states, right? Remember that the energy of a hydrogen atom is only dependent on the principal quantum number. So all the s, p, d, f's, and g's and whatnot, they're all the same energy. It only depends on n. Okay, so if you have a degeneracy, it's possible that you're going to run into a situation where the denominator is 0, and anything over 0 is going to be infinity, and there's no fixing that, right? So you can see that you clearly have a problem here. Okay, and so I mentioned examples. Okay, so what to do? Okay, what to do? Again, the derivations and the explanations I've seen are shockingly difficult to understand. And it's I hate to see that, because what they whittle their explanation down to is the most simple thing possible. You make V diagonal in the basis set of the unperturbed states. Okay. So at this point, remember test two. Remember test two, where I had the time evolution operator, and you had to put it in matrix form. And a lot of you had trouble, but I hope that you don't have trouble now, because a lot of you got beaten up on that. You know how to write operators in a matrix form, which of course is dependent on the basis, so you know how to do that. What I'm saying is take the unperturbed wave functions, create a potential energy matrix, and diagonalize it. Get this, the energies of, so you would write that in MATLAB, you just write a matrix in MATLAB. What are the energies, right? What are the eigenvalues? You can ask for the states as well. Again, we tend not to worry about that so much. First order corrections are good enough. So we create this matrix, diagonalize it, ask for what are the eigenvalues, and those are your first order corrections. So it ends up being really, really easy because remember, we were making matrices out of operators a long, long time ago. Okay, so what are we going to do here? Okay, now the best way to do this is an example. And we're going to have an H atom in an electric field. And we're going to put this in the Z direction. Okay. So what that means is that the perturbation is going to be an electric field. I'll give that the letter E with a hat. It sucks, right? E is energy, but you really don't have a choice, but E is also an electric field. So you just get two plates and charge them up, and you get a hydrogen atom in between, and people have literally done this a long time ago. So I've always noticed that when E is an electric field, you put a little vector hat on it, and that's how people try to make sure that you know what you're dealing with. Okay, we all know that the nucleus, and here's the electron. They are, of course, here is R. Here is the radial coordinate. The potential energy formula is, of course, minus the dipole moment times the electric field, which is in the Z direction, so I won't put a hat on that anymore. The dipole is dipole moment is minus E, the difference in charge, which would be E times R, and charge minus charge times distance, therefore minus minus is plus, and so what you end up with, the perturbation energy, is the charge of the electron, the strength of the electric field, again in the Z direction. Now you still have an angle part because you've seen here the electron is like whizzing around, right? So cosine theta. Theta, of course, is the coordinate for the electron. That's the angular coordinate of the electron. You can see why we line this up in Z. We want to align the electric field in Z because it makes it convenient that not only is it a natural angular description of the electron, it also tells you how it's displaced with respect to the electric field in angular terms. So it's way more awesome to do it this way. Okay, now in matrix form, you got to remember that your basis set is, an electric field that has a direction, a linear electric field, will not affect an S state because an S state is the same all the way around. It's going to affect a P state. In fact, it's going to affect a PZ state. It won't affect an X or a Y state because of it just doesn't. Okay, so to some degree, you have to take it for granted. That's how it works. Now I'm also going to work. So we have to work in the n equals 2 state. because there's no p states for the n equals 1 state. And I'm going to work with pz. Remember that p0 is the pz state. And then we've got p plus or minus 1. Plus or minus 1, of course, are the subquantum number, m sub l. Remember that px and py are linear combinations of plus and minus. We don't need to worry about that, but sometimes, just be a little careful, sometimes it matters. Now again, the electric field is going to affect the z state, but it actually doesn't affect x and y. So it's a little funky, but that's how it works. Okay, so the matrix, and you can work all this out, but let me just show you the result. And so I have to write the kets on top, and then I have to write the bras on the other side. And now you should know what the integrals look like in between. Okay, so it turns out that again, a linear electric field can't affect something that's round. It just doesn't. Okay, now it will affect the pz state. And the Hamiltonian should be symmetric. Remember, that is a property of hermiticity. Oh, I should put bracket signs. That is an effect of hermiticity. These have to be the same number across the diagonal. And they can be imaginary too. And if they're imaginary, this one's equal to minus that one. If they're real, they're equal in sign and magnitude. If they're imaginary, they're equal in magnitude but opposite in sign. Okay. So here's the matrix. And again, you could calculate all of these, or you could use like some kind of knowledge of symmetry, like group theory, to know that basically all the matrix elements are 0 except the z and the s and the 2s thing. Now what that means is, by the way, you don't need, now you've been doing enough with matrices to know that this is block diagonal form. And so what you can do is just create a 2x2 matrix and solve that. All these other zeros literally do nothing. So what we want are the eigenvalues and eigenstates if you want to do corrections to the wave function. But really we want the eigenvalues of this 2x2 matrix. Okay, now I'm telling you, degenerate perturbation theory is way easier than regular perturbation theory. Because I mean seriously, we've been doing this for a while. It's just a little bit more difficult because I'm using a hard example. That's really what it comes down to. Okay, now let me point out and to emphasize that this is a little difficult. I'm actually going to really stick it to you. Now, recall that you may be thinking like, oh, okay, all right, I understand a matrix, but what does it mean to have the ket of the p state and a bra of the s state? Wait, what does that mean? Okay, now for one, this is simply how you write matrices. We know that. This is how you write matrices in your basis. But in case you forgot what that element looks like, it would look like this. Again, this is a z state. Okay, so that's what that means. All right, now let me write this thing out in all its glory. Electric charge, strength of the electric field, so that can be varied. And now the dipole, remember, oh, did I forget something here? I think I forgot something. I forgot. Did I forget R? I have to double check this. I think I forgot. Sorry about that. I think I forgot an R. That would be in case the electron, remember the electron is not a particle in a string. You can breathe a little bit. So that would change the dipole moment. So that should be there. Sorry about that. It'd be charge of an electron, charge of the applied electric field. Now I've lost my notes. Okay. Psi 2s, which is a little complicated. There's no R1 or R2 in here because there's only one electron. 2p naught, again, notice the 2pz state, Notice I don't have a 4 pi E naught. I don't have that because what I'm going to do is I'm going to need to include explicitly the angle parts, and that is because of this cosine. And so let's see here. I've got, oh, that needs a little star. Not that it matters. They're not complex. Okay, because there's an angular component, I need to use the angular wave functions. Okay, so this is the P state. Remember that is the spherical harmonic. Here's our perturbation. Here is the S state. Actually, I should have switched those, shouldn't I? I should have had the S state. I should have had the S state over here. The way I was doing it, doesn't matter, by the way. I just want to. I want to do this exactly right. Okay. L of 1, M of 0, sine theta, d theta. Almost ran out of room. Okay. Now, again, this is just an exercise in Mathematica. And again, at this point, I hope that you're really quite conversant. And so, yeah, I'm not going to even worry too much about this. So this ends up being, let me remind you, this is still the potential energy. So it's -3 times the electric field times charge of electron, applied electric field, times A naught. Oh, if we want to be careful about matrix 0, 1, 1, 0. Again, the off-diagonal elements have to be the same, or this is not Hermitian. And then all right, you plug this in the MATLAB, now you know, okay, use applied, use atomic units, that's one. Then you have to figure out, okay, that would be a pain, right? You'd have to figure out how to put the electric field in atomic units. Good luck with that. I'm not sure how to do that conversion. The eigenvalues are -+3 times the electric charge times the electric field times A naught. And the states are actually hybrid. So what these are SPZ hybrids. So you get the 2s state, and you make a 1-to-1 combination. The square root of 2 is just me normalizing it. You'd have to normalize it after the fact. Okay, now don't be confused by this minus plus. What that means is that for the wave function, that's 2s plus 2p naught. That would probably look like this, right? When you add those two constructively, you're going to lower the energy. And notice that I've got the z direction versus, then the other guy would do the exact opposite, right? So that would be hybrid energy. The electron's going to respond to the electric field by moving up or down with respect to whichever plane is positive. The way that would look in terms of a diagram, an electronic energy diagram, would look like this. So again, 2s, 2p naught, which is pz, 2p1, 2p minus 1, which you make linear combinations of to make minus things. You make linear combinations. These are the unperturbed pz plus or minus 1 states. And then you've got the plus. Again, as referred to the wave function here. Now you can see why that energy has that weird minus plus symbology there. So that's really about it. Again, I just want you to know that this exists and that degenerate perturbation theory is not the same as perturbation theory. That's all you need to know. If you ever need it, you're going to have to look all this up. You just need to know you need to look it up. That's kind of more important than anything. You see how it works. I also like the fact that we got that into some atomic orbitals and whatnot. We're going to do a little bit more of that this last week. The last bit I wanted to mention, it's on the syllabus, but we've actually already covered it, is variational theory. And I'm really out of time, but I'll just mention a quick word about it. Variational theory. Okay, variational theory it was also on problem set 4, so we've already covered it. What it is because we don't know the proper wave functions for like helium, it means that whatever wave function you use will always be higher in energy. Okay, so the way that works is you have a guess wave function, so let's use Dirac notation for that, which is referred to like this, and the energy would be this. Now, I mean, at this point, this is like stupid. Why am I writing a matrix element with the Hamiltonian? Because I want you to see that this is something that I've largely been ignoring. This is called an overlap integral. Overlap integral. Okay. Now, what this is you're not sure that the thing is normalized. So, because your guess may not be normalized, you need to normalize it. This is universally expressed in these types of quantum mechanical calculations, so I want you to see it to know that when you see these types of discussions on wave functions, on molecules, for like programs like Gaussian and whatnot, you'll always see the overlap integral. It ends up being important also in Coulomb interactions for electrons between atoms, which we never covered. Overlap integrals are actually very important. So I wish I had more time to talk about them, but whatnot. Now, it turns out that this is always it's always greater than the real energy. This is always greater than the real energy. And that has to do with the fact that you can write the guess wave function as a linear combination. Remember, this is what it means to span all states. The guess wave function can be written as a combination of the actual wave functions that you don't know for various reasons, like the electron-electron interaction. So we're going to say that these k states are the real wave functions that we will never know what they are. But your guess wave function can be written as a linear combination of these forever unknown wave functions. Now, because because the ground state is always the lowest energy, and there's only one ground state, this sum inherently involves higher energy states. So when you substitute this into here, this is how the proof works. There's always a contribution to a higher energy state, and that's why you always have to have a resulting energy that's higher than the ground state. So that's why that works. When it comes to variational theory, you should know that it's very important when you start to learn numerical methods like Hartree-Fock. Hartree-Fock is variational. That means that the energy is always greater than the actual energy. What's good about that is that it's trustworthy. You can always trust that the energy is too high. You might need to know that. The methods that are considered robust are variational. The methods that are non-variational, which includes density functional theory in certain forms of perturbation theory, like molar plecid perturbation theory, I'm guessing about that, I may not be right about that, but I'm pretty sure I am. Molar plecid perturbation theory, these you will hear if you get into computational theory. Those are non-variational. Be careful when you use those. When you use a non-variational theory, you're considered to be treading on thin ice. You're probably still going to use them, but know that it's important to realize when you're using a variational theory and when you're not, and what that means. Okay. With that, someone is trying to get into the door, so we're now going to go backward in time to do the first lecture. I'll see you all in 1 minute.